All right, hello and welcome to lecture this evening. We are going to be continuing in chapter 4, but before we do, I want to talk a little bit about our first exam, which is coming up. And lab. There's a couple logistical announcements, but I am pulling up the information on Canvas just to make sure. I get everything right. Okay. So a couple things. First off, so before we dive into lecture, I want to speak for a minute about exam 1. It was originally and I will correct this in Canvas. The announcement that I said, I gave the wrong date, or I gave the right date but the wrong day. So our first exam was originally going to be on this Thursday, but I'm bumping the exam date to March 2nd, which is a Tuesday, not a Monday. I said Monday, March 2nd. Monday is, March 1st. March 2nd is a Tuesday, and that is when exam 1 will open. And I posted a breakdown of exam 1, kind of like a guide for preparing for it on Canvas. But the important thing to know is exam 1 covers everything including Ionic nomenclature. Which is naming ionic compounds. We're going to begin our discussion of ionic nomenclature tonight, and we will be finishing it on Thursday. So that will be the last topic on the exam, and so it'll cover everything in there. There's one thing that I wanted to mention, because I give the breakdown of all the different problems that are topics that are going to be on the exam: unit conversions, density, isotopes, periodic table, electron configurations, atomic mass, orbital diagrams, ionic charges, and naming ionic compounds, which is what we're going to start tonight. There's one topic that is not on that list that you will get tested on over and over and over on this exam. And that is significant figures. The reason why it's not on the list is because there will be no problems structured like how many sig figs are in this number. Not going to be on the exam. But every mathematical calculation you do on this exam will involve sig figs. And so I just want your mental mentality to be zeroed in on that fact. This is definitely something you want to practice. All right. Now, the second thing that I want to talk about is lab activity 5, which is this week's lab. Now, typically, as you know, the lab activity is, there's a pre-lab that's due before your lab starts, both for Tuesday and Thursday. And then there's an in-lab that's due during the lab period, and then the post-lab is due before lab starts next week. Now, your post-lab for lab activity 5, nothing's changing. But I am changing the structure of lab this week Both the pre-lab quiz, so pre-lab 5, and in-lab, the in-lab activity, both of these are due this Saturday, which, let me just make sure I got this date correct. Yes, I did. So they're due this Saturday by 11:59 p.m. I'm putting them both due at the same time. The reason for this is Lab Activity 5 covers 3 things. Ionic naming or nomenclature, covalent naming, and acid naming. We are going to begin ionic nomenclature, ionic naming in lecture today, but covalent naming and acid naming I'm covering in a lab lecture tonight. So I didn't, because we're a little bit behind schedule. Oh, my 2-year-old is crying. I don't know if you can hear that in the background. Anyways, so we're covering covalent naming and acid naming in a lab lecture tonight. I didn't want, because we're a little bit behind in lecture, it wasn't fair for me to say, here's a pre-lab on a thing that I haven't taught you yet. So as a result, what I'm going to do is I'm going to talk about both of those subjects tonight in lab. And you can watch live. You don't have to watch live. Thursday lab people, you can watch it on Thursday, or you can tune in live tonight. But I'm going to cover those things, and that way, between lecture today and Thursday, and then between the lab lecture tonight on covalent naming and acid naming, you'll be able to do all the nomenclature stuff. So you'll be able to take the pre-lab quiz and finish the in-lab assignment by this Saturday. And if you're antsy about it, because you're like, it's this assignment and I need to be studying for the exam, the cool thing is ionic nomenclature is a significant portion of the upcoming test. It's 25% of the upcoming test, to be exact. And doing these worksheets will help you study for that portion of the exam. So you can kind of kill 2 birds with 1 stone. So anyways, I posted all this on Canvas, but I just wanted to take a few minutes at the beginning of lecture, give everybody a heads up as to the game plan. And yeah, that's what I got. So let's go ahead and dive in to where we left off in lecture on Tuesday, and we were talking about ions. Just by way of review, a cation, cations are positive, right, where you have a net positive charge. Anions are negative ions. All right, they have a net negative charge. So a cation has more protons than electrons, an anion has more electrons than protons. All right, and so we know what ions are. We talked about this last week, but it begs the question. Oops. Why do ions form? Right? Why do they form in the first place? Why don't elements just say neutral, right? It sounds balanced, positive and negative. And the reason why ions form, the answer to that question lies in the periodic table. Specifically, it lies in the last column of the periodic table. All right, these are the noble gases. All right, these are the noble gases. And they are, let's see if I can draw a better rectangle. Yeah, it's slightly better. They're the reasons ions form. You're like, how's that? Well, the noble gases are called the noble gases because they are incredibly stable. All right, and as we'll discuss as we move throughout the semester, another word for stable is unreactive. All right, unreactive. These things are stable, they don't react, they're like all zen blissed out, right? And so their deal is they don't react with anything, they're inert. They're actually one of the last groups of elements on the periodic table to be discovered because since they don't react, they're not products of reactions and they're not reactants in reactions. They don't engage chemically with the rest of the periodic table. And it turns out that every main group element wants to be a noble gas. All right, every main group element wants to be a noble gas. And the key to their stability, all right, what makes them so stable, the key to this noble gas's stability is their electron count. All right? Noble gas stability comes from their electron count. And every other element, every other main group element, is willing to steal electrons or give their electrons away in order to have the same electron count as their nearest noble gas. All right? So when you look at the noble gases, let's look at helium. If we wrote out the electron configuration for helium, it would be 1s2. If you look at neon, neon would have an electron configuration of helium, right? It's its nearest noble gas with fewer electrons. The neon is 2s2, 2p6. Argon has neon for its noble gas abbreviation. It is 3s2, 3p6. Krypton has argon for its noble gas abbreviation, and it is 4s to 3d10, 4p6. Now, let's do one more. Let's do xenon has krypton for its noble gas abbreviation. Its electron configuration is 5s2, 4d10, 5p6. Now, there's a common theme here. When you look at the valence electrons, so those are the electrons in the highest energy shell. Neon has 2 in its s subshell, 6 in its p subshell. So that's 8 electrons in its highest energy shell. Argon has 2 plus 6. So that's 8 valence electrons. Now, krypton also has 8 valence electrons. Remember, the highest energy shell here is the 4th shell, and there's only 8 electrons in the highest energy shell. So still 8 valence electrons. Same deal with xenon. When you look at its highest energy shell, which is the 5th shell, it's got 8 electrons. The only noble gas that kind of wrecks this curve is helium. Helium only has electrons in the 1st shell, so there are 2 valence electrons for helium. So that's helium's a little different, marches to the beat of its own drum. But if you look at it, we've got 8, 8, 8, 8. That's why the guiding principle for ion formation is known as the Octet Rule. Which states that every main group element wants the same electron count as its nearest noble gas. And that electron count will usually involve 8 valence electrons unless it's closest to helium, which only has 2 electrons. All right? So we can use this, the Octet Rule, to solve problems like the following. So for example, oops. There we go. For example, let's determine the ionic charge for the following elements. All right, determine the ionic charge for the following elements. Now, let's start with oxygen. All right. So if you're going to determine the ionic charge for oxygen, you need to locate and compare it to its nearest noble gas. And for oxygen, that nearest noble gas is neon. All right. And neon has 10 protons and 10 electrons, because that's the atomic number. Now, when oxygen is an element, it has 8 protons and 8 electrons. All right? Now, oxygen is willing to become an ion if it means having the same electron count as neon. So when oxygen, to get that same electron count, oxygen needs to gain 2 electrons. So oxygen, when it becomes an ion, will still have 8 protons. The proton count never changes for an element. That's what makes oxygen oxygen. But it's going to upgrade its electron count to 10. And you'll notice now we have 2 more electrons than we do protons. So our ionic charge is a -2. right? Our ionic charge is a -2. Let's do another example. Let's determine the ionic charge that bromine will develop. All right? Bromine is right here. It has 35 protons and 35 electrons. Bromine wants to be like krypton, which has 36 protons and 36 electrons. All right, so when bromine upgrades its electron counts, it'll still have 35 protons because that's what makes it bromine. But when it upgrades to 36 electrons, now it has one more negative charge than it has positive charges. So it'll have a charge of -1 because that's the difference between these two. That's the imbalance. Let's do another example. Let's do magnesium. Magnesium is right here on the periodic table. It has 12 protons and 12 electrons. Now, magnesium's nearest noble gas is not argon, it's neon. Argon has 18 electrons, but neon has 10, so it's actually closer. 10 protons and 10 electrons. Ariana, the reason why I knew that bromine had 35 electrons is because that's the number on the periodic table of bromine. It's element number 35, and that's the number of protons in its nucleus and electrons it has when it's a neutral element. When it's an ion, that's not the case. But the atomic number tells you the number of protons and electrons for the neutral element. That's also how we knew that magnesium was 12. Now, magnesium will become an ion to be like neon, and to do so, magnesium needs to lose 2 electrons. It wants to have 10 electrons, just like neon does. But now you can see that when magnesium has 10 electrons, it's lost 2. It has more protons than electrons, so magnesium's charge will be a +2. All right, so sometimes elements gain electrons to become like their nearest noble gas. Sometimes they lose electrons. Ariana, my pleasure. Totally my pleasure, and you're so totally welcome. All right, now that we've had an introduction to why ions form, how they form, we need to talk a little bit about, well, now we can start talking about naming them. All right, so we finally get to crack open the topic of ionic nomenclature. All right, so first off, here is how you name ionic compounds. When you have an ionic compound, Brandon, that is correct. Spot on. All right. Let's talk about naming ionic compounds. So when you have an ionic compound, the way you name it is you write the cation name, followed by the anion name, and then you chop off the end of the anion name and add IDE. IDE. All right. The way to identify that you have an ionic compound is you'll have a metal together with a nonmetal. And that is the indication that you have, that you're dealing with an ionic compound when you see a metal paired with a nonmetal. As we'll see a little later, there is an exception to this. 98.7% of the time, it's going to be metal and nonmetal. And so just roll with me on this one, and then you'll see, I'll point it out when we get to the exception to this rule. And you'll be like, oh, that's not that bad. Because it's not. But we're just going to assume metal together with a nonmetal. And you'll see the exception when we get there. All right, so for example, let's name this compound. All right, if we, and actually, let me pull up our trusty periodic table. Maybe downshifted a little bit. There we go. So you'll notice here, so let's name this compound. I almost just said its name. You'll notice that our first element is definitely a metal. Our second element is a nonmetal, so we're dealing with an ionic compound. The metal, the cation's name is sodium. The second element, Cl, is named, that's the name of Cl is chlorine, but the trick to naming it is you chop off that end and write ide. So Daisy, spot on. The name of this compound is sodium chloride. Let's do another example. Let's do, how about, AKA, yes, Blake, correct. Let's name, let's name, I almost said its name. First thing to spot, we have a metal together with a nonmetal. So ionic compound for sure. The name of our metal, our cation, is magnesium. And the name of our anion, or nonmetal, is bromine. But then we chop off the end and add an ide. So this is magnesium bromide. Oops, sorry, I messed up my chemical formula. It's MgBr2. And actually, I'm glad this happened. You'll notice that for sodium chloride, there was just one sodium, one chloride. For magnesium bromide, there's one magnesium, two bromides. Doesn't change the name. Naming ionic compounds is the simplest type of naming because it's just, you don't have to worry about numbers. It's just metal, non-metal, cation, anion. You don't have to worry about how many there are. We'll talk about why in just a minute. Let's do one more example. Let's name this ionic compound. All right, again, we've got a metal together with a non-metal. Aluminum is touching that kind of zigzag track, so it's like in that metalloid region, but it's definitely on the metal side, so we're not worried. Our metal's name is aluminum. And our nonmetal's name is oxygen. But again, we chop off the end, add "ide." So the name of this ionic compound is aluminum oxide. All right? Aluminum oxide. Now, naming them, not too bad, right? When you're given a formula, you don't even have to pay attention to the subscripts. You just look at the name. Yep. Heriberto, exactly. It's aluminum oxide, right? Name of the cation, name of the anion. When you're given the chemical formula and asked to name an ionic compound, it's not too shabby. It's a little more work if you're given the name and asked to write a formula. So for example, let's say I asked you to write the formula for potassium bromide. All right. If I asked you to write the chemical formula for potassium bromide. Karen, great question. It's this line on the periodic table. Nonmetals are this region plus hydrogen. Hydrogen's not a metal. And then metals are over here. This side, this stuff, all this stuff, everything on the other side of that jagged pink line. All right. So now let's practice moving in reverse. And here's the thing. Potassium bromide, this is why it's a little trickier. When you're given a chemical formula, it's straightforward. Cation name, anion name. And it's simple because the name doesn't inherently contain any information. Karen, you're so totally welcome. The name doesn't contain any inherent information about the number of each anion and cation present. But when you just see this name, you don't know if it's KBr, you don't know if it's KBr2, you don't know if it's K2Br, K3Br. Oh, I just wrote an R, that's confusing. Right? How do you know? And this takes a little more thinking, but we can do it. The thing you got to remember is all ionic compounds are what we call net neutral. All right. Another way of saying this, what net neutral means is the total positive charge plus added together with the total negative charge will always be 0. So all your positives plus all your negatives always adds to 0 for every ionic compound. And that is how we're going to find the formula for potassium bromide. So what we have to do is we have to find out what kind of charge does potassium have, what kind of charge does bromide have, and then balance the two together. So if you look at potassium, potassium is right here. It's number 19. It wants to be like argon, which has 18. So potassium as an ion will lose, or I should say, sorry, potassium as an element has 19. It wants to be like argon, which has 18 electrons, so it is going to lose 1 electron. And if it's lost to a negative charge, that means it will have a charge of positive 1. Bromide has 35 electrons. It wants to be like krypton, which is 36 electrons. So bromine is going to gain 1 electron to become bromide. If it's gaining 1 negative charge, it will have a charge of -1 because our positive charge is +1 and our negative charge is -1. That means potassium and bromide will come together in a 1-to-1 ratio. So potassium bromide must be KBr. So not KBr2, not K2Br, not K3Br. Potassium bromide is KBr because our positives and our negatives always have to balance each other out, right? Another way of saying this would be our +1 added together with our -1 comes out to 0, net neutral. All right, let's do another example. The only way to get used to this is just getting reps in. So let's determine the chemical formula for sodium sulfide. All right, first we have to figure out what kind of cationic charge we're dealing with. Sodium has 10 electrons. It wants to be, sodium has 11 electrons. It wants to be like neon, which has 10. All right, so if it wants 10 and it has 11, it needs to lose 1 negative charge. Yes, totally. This is where the algebra comes into play. So sodium's going to lose 1 electron, which means as a cation, it will have a charge of +1. Now, sulfide is the anionic version of sulfur. Sulfur has 16 electrons and wants to have the same electron count as argon. So, not Ar, right? It's sulfur. Sulfur has 16, it wants 18, it needs to gain 2 negative charges, so it will have a charge of -2. All right, so now we need to balance our charge of +1 together with our charge of -2. So how many positives do we need to balance this negative? And the answer is 2, right? To balance our charge of -2, we need to bring 2 sodiums to this party. So the chemical formula for sodium sulfide will be Na2S, because we need 2 positive ones to balance with our 1 -2. All right, let's do actually it's the other way around. And the reason why, let's pause for a moment and think about the reason before diving into the next example. If we just had, the reason why we need 2 sodiums is because the charge for sodium is +1. And the charge for sulfur is -2. And we need this expression to add up to 0. You need all your positives to cancel with all your negatives. So we need 2 positive ones. That's why it's Na2 S. Okay, let's do another example. Another way to think of it, it's because 1 goes into 2 twice, right? 1 goes into 2 twice. Now I'm going to give you, in this next example, the hardest version I can throw at you. All right, this will be the hardest type of, here's a name, determine the formula. Determine the formula for calcium nitride. First, let's look at our cation. Calcium has 20 electrons. Its nearest noble gas is argon with 18. So calcium needs to lose 2 negative charges, which means it will pick up a charge of positive 2. Let's take a look at nitride. Now, nitride is the anionic version of nitrogen. Nitrogen wants to be like neon. Nitrogen has 7 electrons, neon has 10, so nitrogen needs to pick up 3 negative charges. Oops, not sodium. Which means it will have a negative charge of 3, a charge of negative 3. Now, here's why this is the hardest version. 2 and 3 do not go into each other evenly. All right? 2 and 3 do not go into each other evenly. Before, when we had potassium bromide, right? 1, -1, +1, they went into each other evenly. When we had sodium sulfide, 1 goes into 2 twice. They went into each other evenly, but 2 and 3 don't. So this is the hard version. The cool thing is there is an easy trick when you're dealt this hand. What you want to do is, for your cation, take your anionic charge, which is 3, and make that your cation subscript. Then you take your cation charge, which is 2, and make that your anion subscript. And that is your chemical formula. The reason why this works, if you want to look at it algebraically, 3 times calcium's charge, which is positive 2, plus 2 times sodium's charge, which is -3. Does this add to 0? Well, let's look. 3 times 2 is positive 6. 2 times 3 is -6. It does add to 0, so they cancel each other out. That's the quick trick. When your 2 charges don't go into each other evenly, make your anion's charge your cation subscript, and your cation's charge, make that your anion subscript. And that'll get you the right answer. All right. Now, at this moment in time, you can name any ionic compound with main group cations, all right? But what about the transition metals? We got to talk about transition metal nomenclature. Yep, rocks, exactly. It is the distributive property at work. Transition metals are a little bit harder because they do not follow the Octet Rule. All right? Transition metals do not follow the Octet Rule, and as a result, they don't have predictable charges. They could be anything. All right? Take, I don't know. Take, well, Take iridium, for example. Iridium, which is a transition metal, it's right here. Number 77. Iridium, and this is true for the transition metals, there's no regular pattern for the charges they develop. So iridium can have a charge of +3. It can have a charge of +1, right? You don't know what it could have. Could be either of these. Could be something else. In very rare instances, it can get even higher. As opposed to, like, sodium. Sodium is always +1 no matter what because it is a main group metal, right? When we're talking about main group elements, the octet rule's in play. All right, but the transition metals, it's like the Wild West. There's no telling what it is. Now, this may sound like it's going to be a headache. You might be hearing this and thinking like, oh my gosh, this is going to be such a pain. And it is and it isn't. When you're given a formula and asked to determine the name, it'll make that a little bit more work. But when you're given the name and asked to determine the formula, it'll actually simplify things a bit for you. All right, and here's how. All right, so iridium's in the middle of the periodic table. I cannot tell you, I can't ask you to write the chemical formula for iridium chloride. I can't, because you have no idea what ionic charge iridium will have. You can say, well, I can look at chloride, and I see that chloride has 17 electrons. It wants to be like argon, so it's going to pick up 1 electron, have a charge of -1. But iridium, you have no idea because it's in the transition block, right? It's in the D block. It's a transition metal. I have to explicitly, when I give you a name, I have to explicitly tell you what the charge of iridium is. Otherwise, there's no way for you to name it. So I have to, the way you do this is you put a parentheses after your transition metal and you write in Roman numerals the charge of that cation. So I could ask you to write the chemical formula for iridium 3 chloride because I have explicitly told you that this iridium ion has a charge of +3. All right, when you compare these, -1 goes into +3 3 times, right? 1 goes into 3 3 times. So that tells you that your chemical formula for iridium 3 chloride will be IrCl3. All right, but I have to tell you, if I don't give you that charge, there's no way for you to solve the problem. All right, so with the transition metals, you will always have the charge explicitly given in a Roman numeral. All right? Cation charge is always given. So let's do this again. Let's write out the chemical formula for how about palladium 2 oxide? You don't have to, correct. Because the thing is, the one charge goes into the other one evenly, so that gets you to the answer. You'll notice that, so oxide is our anion, right, based on oxygen. Oxygen has 8 electrons. It wants to be like neon with 10 electrons, so it's going to gain 2. So our anion's charge will be -2. Palladium is a transition metal, and I know because I'm given my charge. So I don't even have to look at the periodic table. I just know that its charge is positive 2 because it's in that parentheses. And here, our positive charge and negative charge are equal. So it's just PD. Oh, there's one of each. +2, -2, they balance. Let's do another example. Let's do zirconium 4 oxide. We'll do another oxide. So again, we just talked about oxide. It's -2, right, based on oxygen and neon. Zirconium, in this compound, has a charge of +4. And again, we have a charge of -2, positive charge of 4. 2 goes into 4 twice. So we are going to need 2 oxygens to balance with our zirconium 4 cation. All right. Now, so this method, as we've seen, it's totally fine. It's a little less work when you are given a name and asked to write the formula, because for main group metals, you had to determine the charge from the periodic table, and for these transition metals, you're explicitly given the charge. Now, if we start doing these problems in reverse, you'll see that it actually takes a little more work. Now I'm going to give you a chemical formula, and you will have to name it for me. All right? So let's do let's name this compound. Now, as always, it's always cation name followed by anion name. So our cation is nickel, and our anion is chlorine, but we're going to add the "ide," right? Nickel chloride, but if you left it there, this would be incorrect. This answer would be incorrect. This is not the name of this compound. And the reason why this is not the name of the compound in question is because nickel is a transition metal. Anytime you're naming an ionic compound that has a transition metal in it, you must include in the name the charge of the transition metal inside a Roman numeral. Or, sorry, the charge of the metal as a Roman numeral inside a parentheses. All right? So we need to figure out what Roman numeral goes in there. It's not enough to say nickel chloride. We have to explicitly state its charge. Now, if you're wondering, how do you calculate that? Here's how. You have to set up an equation. We know that the charge of our 1 nickel plus the charge of our 2 chlorines has to add to 0 because every ionic compound is net neutral. All right? We do not know the charge for nickel, but we do know the charge of chloride, or we can find out the charge of chloride. Chlorine is right here on the periodic table. It's got 17 electrons. Its nearest noble gas has 18. So chloride, has a charge of -1. So we plug in -1 for chloride, and this equals 0. All right, so if nickel, the charge on nickel, -2 equals 0, then we can solve for the charge on nickel by adding 2 to both sides of this equation. So the charge on nickel in this compound is positive 2. All right, positive 2. So this is nickel 2 chloride. All right, the name is nickel 2 chloride. Let's do a couple more examples. Okay. So how about we do, okay, so here's the deal. So let's name nope. Oh, here we go. One, two, 1, 2. Is the okay, hang on. Is the sound on at this point? 1, 2, 1, 2, 1, 2. I'm showing that it's registering in the desktop. Okay, solid. Dudes, thank you so much. Because I don't know why that happened, but it did. Okay, so here, let's back things up just a step. So, oops. Okay, so okay, I'm just gonna start this part of the problem over. So again, we have the charge for nitrogen, right? Or the charge for nitride, I guess I should say, -3. So now we can plug it into this equation. So we have 2 times the charge on nitrogen, -3, equals 0. And now we just got to do some algebra. So we have 3 times the charge on mercury plus 2 times 3 is 6 equals 0. Now we have to isolate mercury on one side. Oh, sorry, with this equation, I made a mistake here. It's not a positive 6. It is a -6 because it's 2 times -3. So we need to add 6 to both sides of this equation in order to solve for the charge on mercury. So we have 3 times the charge on mercury is equal to a +6. And to solve this, so we have 3 times the charge on mercury is +6. To solve for the charge on mercury, then we divide both sides by 3. And our charge on mercury comes out to be a +2. And we put that inside the Roman numeral next to mercury. All right, so we have, oh my camera just started going out. Oh, there we go. It's a little more light. Okay, so that is our charge for mercury. So the name of this compound then is mercury 2 nitride. All right? Mercury 2 nitride. Now, so that's transition metals. They just take a little bit more work if you're given the formula and asked to name them, because and this is really what you got to remember. You always include the charge as a Roman numeral inside a parentheses next to the cation. All right? Now, there's only one last thing to talk about, and then you will have ionic compounds locked and loaded. And you'll be able to handle any ionic nomenclature that I throw at you. So the last thing that we need to discuss is something called polyatomic ions. And actually, our periodic table can peace out for the moment. All right, polyatomic ions are a special class of ion. Up to this moment in time, all of our ions have been monoatomic, meaning that every ion we've looked at has only had one atom present. All right, so it's sodium has been +1, chloride has been -1, right? Polyatomic ions are ions, simply put, they're ions made up of more than one atom. Right? That's why they're polyatomic. They are a group of atoms. They're a group of atoms that share a charge. All right, and each polyatomic ion has a special name, a specific name associated with it. Now, I would, if we were meeting under normal circumstances, and what is normal if I'm being real anymore after 2020, but if we were meeting in a traditional classroom and you were taking exams in class, right? I would tell you you'd have to memorize these. This is something that I require my students to memorize because they are that important to know. That being said, as you know, my exams are open, everything. So you can consult the internet, book, lecture notes, what have you, while you're taking the exam. So I would strongly suggest if you memorize them, it will make these problems go faster. So I still advocate memorizing, or at least add these to your exam sheet because you're going to need them at the ready. All right, so memorize or exam sheet, whichever you prefer to do. So there's a ton of polyatomic ions out there. And you'll see in the pre-lab quiz and the in-lab worksheet for this week for lab activity 5, there are polyatomic ions. There's a reference sheet with a ton of polyatomic ions on there that you will have to use for that sheet. The ones that I'm going to give you right now are the only ones that are going to show up on an exam. All right, so these are the ones that you'll be tested on the exam. The lab activity involves a broader range of polyatomic ions, but these are the ones for the tests. So the first polyatomic ion is NO3. So it's 1 nitrogen, 3 oxygens with a charge of -1, and the name of this polyatomic ion is nitrate. Then there's NH4 with a charge of +1. This is ammonium. Next is SO4 with a charge of -2. This is sulfate. Followed by HSO4 with a charge of -1. The name of this is bisulfate. Also known as hydrogen sulfate. This is bisulfate or hydrogen sulfate. Next, there is PO4 with a charge of -3. This is phosphate. There is HPO4 with a charge of -2. This is biphosphate. No, sorry, not biphosphate. This is hydrogen phosphate. The bi thing is just for sulfate. And then there is H2PO4 with a charge of -1, and this is dihydrogen phosphate. We have a few more. We have CO3 with a charge of -2. This is carbonate. HCO3 with a charge, not of -2, of -1. This is bicarbonate. Or this also goes by the name hydrogen carbonate. CN with a charge of -1. This is cyanide. H3O plus is a positive polyatomic ion. Goes by the name of hydronium. And finally, OH, the charge of -1, is hydroxide. All right, and something that I have to stress is the atomic order in these is important. And I don't know why, but I run into this problem a lot. Hydroxide is OH with a charge of -1. it is not. Like, don't ever write it HO with a charge of -1. This is always wrong. All right, and if you're wondering why it's wrong, it's the simple fact hydroxide ain't no ho. Okay, it's OH. It's not HO. So don't ever do it like that. All right, these are the polyatomic ions, they don't add anything to. There's no special way to name them like there is with the transition metals. Right, the transition metals, you have to calculate the charge and include that in the name. When you're dealing with an ionic compound that has a polyatomic ion, you name it just like anything else. It's cation charge, cation name, anion name, and that's it. So there's no special augmentation to nomenclature brought by these, but other than each polyatomic ion has a specific name. So, for example, I'm going to have to clear this board. You might want to leave it open. Whoa. There's our sound on thing flipping out. Oops. I'm going to have to clear the board to do the next few examples, but let's name the following compounds. All right, so let's name, and I'm actually going to bring our periodic table back because we're going to be using it. Let's name the following compounds. Let's go with NaNO3. Now, we're going to name this just like we do any other ionic compound. Our cation's name is sodium. Our anion's name, NO3, is the polyatomic ion nitrate. So this is sodium nitrate. And that's it. Let's do another example. Let's do same CaCO3. Our cation's name is calcium. Our anion's name, CO3, is a polyatomic ion. This is carbonate. And that's the name. Let's do an interesting one. How about let's name this guy. Our cation name is magnesium. Mg is magnesium. What about our anion name? Well, OH is hydroxide. So this is magnesium hydroxide. One of the things you'll notice, this is the first time we've ever come across a parentheses in a chemical formula. All right, and this is significant. Anytime you have multiple polyatomic ions, in a compound, you include a set of parentheses around it. All right. Yep, exactly. Carolina, that is exactly correct. So you do distribute that too when you're calculating charge. But to just show you have more than one polyatomic ion, you put a parentheses around it, and then you put the subscript of however many you need on the outside. All right. So there's some examples where you're naming. Let's do a few in reverse. So let's do a few where we write the formula for let's do aluminum bicarbonate. All right, well, first, we got to figure out our cation, which is aluminum. Aluminum has 13 electrons. Its nearest noble gas is neon, which has 10. So aluminum, after losing 3 electrons, will have a charge of positive 3. Bicarbonate, you're not going to find on the periodic table because it's a polyatomic ion. Bicarbonate has a chemical formula of HCO3 and a charge of -1. So because we have -1 and positive 3, 1 goes into 3 times, right? So we're going to need 3 bicarbonates to balance with our 1 aluminum. Now, our chemical formula will be Al, because we just have 1. Because we have more than 1 bicarbonate, because we're going to need 3 of them, we have to put it inside a parentheses. So we open parentheses, HCO3, close parentheses, 3. That is the chemical formula. Here's why this is critical. If you don't put that parentheses there, and you just write Al, HCO3, 3, this right here that means 33 oxygens, which aluminum bicarbonate does not have. So you have to throw the parentheses around your polyatomic ion. Otherwise, you're writing the formula to a completely different compound. All right. Every time you have more than 1, you must put a parentheses around it. Let's do another example. Let's write the chemical formula for silver 1 nitrate. All right, silver is not a polyatomic ion. Silver is a transition metal. I know because I was given a charge in a Roman numeral, so I don't even have to look it up. So silver has a charge of +1. Nitrate is a polyatomic ion. You won't find it on the periodic table. You just need to know or have it written down on your exam sheet that it's NO3 with a charge of -1. Because our anion's charge is -1 and our cation's charge is +1, I see that these two go into each other evenly. So this is just AgNO3. All right, and that is the formula. Now, here's the deal. This is something that I see often. Because I make such a big deal out of parentheses, right? Because it's wrong if it doesn't have it. If you have multiple, I will have students who at times will just go, I'm going to throw parentheses around every polyatomic ion just to be safe. Here's the deal. If you do it, but there's only one polyatomic ion in the problem, then it's wrong. All right? You only do parentheses you only do parentheses when there's more than one. Stress on more. You only use parentheses when there is more than one polyatomic ion in your molecule. Alrighty. That brings us to just about the end of lecture. We have covered pretty much all you need to know. Well, actually, all you need to know about ionic nomenclature. So you are capable of naming each and every one of the ionic compounds on the pre-lab quiz and on the in-lab assignment, both of which are due on Saturday. When we come back to lecture on Thursday, I'll do more examples because we've covered each topic, but we should get some more reps in, so I'll do more examples using all these things in play. In lab, so we're going to stop now, come back in about 10 minutes. I'm going to give a lecture on covalent nomenclature, which is pretty easy, and acid nomenclature, which has a little bit more of a nuance to it. So I'm going to lecture on both of those. And with that lecture, you will be able to complete lab activity 5 on your own. Again, you don't have to attend live. If you're in Thursday's lab and you have other things planned tonight, you totally can. You can watch this stream on Thursday. And of course, I'm going to stay live for the whole time. So the front side will be lecture, and I'll timestamp it in the comments. But don't freak out when you come if you don't stay with us live and you're like, it's a 3-hour lecture. It's not. I'm just probably going to lecture for the first half hour to an hour, depending upon how things go. All right. Okay, so that's it for lecture. I will catch you guys all